Good morning. I hope the volume's good. If not, you can adjust it right now. Um, I appreciate your cooperation in this process, and I will do my best to try to present this in a way that would be very similar to class. So this morning we're going to be talking about energy and the laws of conservation of energy. As we get into talking about energy, if I were to ask you about energy, for example, what types of energy are you familiar with, you would probably come up with a long list of different types of energy. For example, you might come up with the energy in fossil fuels. You might say solar energy, wind energy. Those are very popular today. Hydroelectric energy, nuclear energy, and so on and so forth. Um, while those are forms, those are all legitimate forms of energy, what we're going to be talking about mostly in this course is mechanical energy. And the interesting thing is, all those other forms of energy that I just mentioned, if you kind of trace it all back to what's going on, it really comes back to the types of energies that we're going to be talking about. So again, this is a foundational course. This is very important physics that you're learning. And I know sometimes you think that the advanced stuff is the most important stuff, but the foundational courses, your first couple years, are really probably the most important information because everything else that you learn after this builds on this. So as we get into talking about energy, uh, what is energy? Well, energy in physics, an object has energy if it has the ability to do work. And work in everyday life, what one person calls work, another person may call play. For example, some people consider gardening very relaxing. Other people would consider gardening hard work. Well, in physics, the definition of work is very specific. The work done in a physics problem is the force acting on the object dotted with the displacement vector while the force acts. So work is a scalar product or a dot product between the force and the displacement while the force acts. Notice here that we're using a d for displacement because we're only dealing with the displacement vector while the force acts. So before, when you were using displacement vector, delta r or delta x, we were dealing with a situation where the displacement maybe was throughout the problem. But with work, we need to be careful that we understand that it's the force times the displacement while the force acts. So, for example, if a person takes a slap shot with a hockey stick at a hockey puck, uh, the force may only be applied while the hockey puck moves a short distance. And then after the hockey stick is done hitting the puck will zoom off and the displacement could be quite large. But the amount of work done is the scalar product or dot product between the force that's acting on the hockey puck times its displacement while that force acts. So here in the equation, you can see work is a dot product or scalar product. If you remember your rules for scalar products, you could also find the size of the scalar product by taking the size of the force vector times the size of the displacement vector while the force acts times the cosine of phi, where phi is the angle between the force and the displacement while the force acts. So work is a scalar. It just has a size. It does not have a direction. It is not a vector. It just has a size. Its size can be positive, negative, zero, anything. So it can have a polarity. Work does have a polarity. Positive work is different than negative work, as we'll see here in a little bit. But work is simply a scalar. So that's one of the nice things you'll find about energy here is energy deals less with vectors and a little more with direct quantities in terms of, it's almost like, as you'll see here as we go along, it's almost like dealing with a bank account where you have deposits and withdrawals and balances in your accounts as far as money. The work energy concept and conservation of energy in physics, if you can relate to a basic checking account, then you'll understand this concept of work and energy as we go along. Now again, taking a look at this diagram, we see an angle between the direction of the applied force and the displacement while the force acts, and the angle between the two is the angle phi. So the amount of work done can also be thought of as the parallel component of the force along the direction of motion. So as this block moves from left to right along the displacement d, as shown in the figure, the force is acting at an angle, but the parallel component of the force along the direction of motion is F cosine phi. And so F cosine phi times d, that displacement length while the force acts, is the work done. Okay, and this shown in the diagram here is an example of what we would call positive work. All right, the units for work in the international system, as you saw on the previous slide, is the joule. Okay, the joule is the unit of work and it's the unit of energy, because work is basically giving or taking away of energy. Okay, that's essentially another way you can think of work. You're either giving energy to an object, which is positive work, or taking energy away from an object, which is negative work. So work is equivalent to like a deposit or a withdrawal in terms of your checking account. The amount of money in your checking account is equivalent to the amount of energy the object has or the system has. Okay, so again, the units is called the joule, named after James Joule. Okay, so here we see a very similar diagram. The force here is shown as a pushing force, and of course the rules would be the same for that. We would take the parallel component of the pushing force, which is shown down here. That's a symbol for a parallel component of a force. So the parallel component of the force, which is F cosine phi, times the displacement represented with the D. So in this case, the work would be considered positive because we would be giving energy of motion to the object. So again, when F parallel and D are in the same direction, we have positive work being done. When F parallel and D are in opposite directions, we have negative work being done. So let's consider a practical example here. Let's suppose your car breaks down. You're driving along, you have a friend in the car, and your car breaks down. So you say to your friend, hey, hop out, and I'll put the car in neutral. You push the car from behind, and we'll push the car off the road. And so your friend gets out and goes behind the car and starts pushing on the car. You put the car in neutral. And so as they push in the forward direction and the car starts to move, your friend is giving energy to the car. So this is an example of positive work being done. And at this point, then you're turning the wheel and turning the car off the road. As you get off the road, let's suppose your car's in pretty bad shape, and so you go to hit the brakes and you realize, oh my gosh, the car's brakes aren't working. So you tell your friend, run up in front of the car and push on the car now to stop it. And so your friend runs up in front of the car, okay, and they start pushing on the front of the car as the car is kind of moving towards them, and they're pushing the opposite direction. Now they start to slow the car down. They're taking energy away from the car. This is an example of negative work. Okay, so positive work is giving energy to something. Negative work is taking energy away from it. Another interesting thing to notice here is that because we measure work or calculate work as the force times the displacement of the object while the force acts, there is no work done if the force is acting in a direction that is not along the direction of motion. So if the force acts perpendicularly to the direction of displacement, then no work is done, because the angle phi would be 90 degrees, and cosine of 90 degrees is 0. So for example, if I slide a bead along a table or along a wire, I guess it shows in this diagram, if I slide a bead horizontally along a wire, gravity, of course, is perpendicular to that direction if I'm sliding the bead perfectly horizontally, and therefore gravity would do no work in this particular situation. Likewise, no work is done if the object does not move. So if the object is, if somebody tells you to hold your physics book out in front of you, and you hold your physics book up in your hand, and the physics book has a weight of 20 newtons, and you hold it up steady for 30 seconds, you may start to become tired. You may feel like you're doing work. But how much work have you really done on the book during this time? And if you're following along and understanding this correctly, you'll realize that there is really zero work done. Okay, because even though you're applying a force and your arm may get tired holding your physics book out, no work is being done on the book because the book is not moving. It is not being displaced along the direction of the force. So in physics, again, remember, work has a very specific definition, and it can be a little different than what you might suspect it would be in everyday life. Because in this case, of course, there's energy being consumed in your body. There's molecules breaking down to provide energy to make your muscles contract. And so inside your body, there may be work being done, chemical energy being expended. But as far as physical work done on the book, if the book is not displaced, then there can be no work done. Okay, so let's take a minute here and just check your understanding of things. I have a diagram on the left where a person is lifting a barbell up, so they're pushing upward and the barbell is moving upward. And then on the right, I have a view of the person bringing the weight back down. So the weight's coming down, but they're still pushing upward in that rightward diagram, right? I mean, if you've ever lifted weights, you know that even while you're bringing the barbell down, you're not pulling it down. You're still supporting it upward. You're pushing upward, and you're letting the weight come back down. So what I want you to do is just take a minute here. You can pause the video, pause the lecture, and answer the questions. Just the sign of the direction of the force, the barbell movement, and whether the work is positive or negative. Okay, so hopefully you got the answers to that right. While the person on the left is lifting the barbell, they are putting a force in the positive y direction. The barbell is moving in the positive y direction. Since those are in the same direction, the man is giving energy to the barbell. He's lifting it up to a higher height and giving it energy, which means he's doing positive work. In the picture on the right, the direction of the force of the man on the barbell is still upward in the positive direction. The barbell is moving downward in the negative direction, and so therefore the work being done here is negative. The man is taking energy out of the barbell. It makes sense because there's another type of energy here we haven't talked about. Energy of motion is pretty intuitive, but there's also the energy associated with a heavy object up at a height, and obviously if the man were to drop the barbell from a higher height, it would have more energy as it hit the ground than if he dropped it from a lower height. So it makes sense that when he lifts the barbell up, the barbell has more energy. He has given it extra energy, and when he brings it back down, he has removed energy from the barbell and done negative work. So now let's get a little more specific about these different types of energy we've been talking about. In the last slide, I kind of alluded to this other type of energy associated with objects up at a height. Well, the first type of energy we've been discussing, the one that's a little more intuitive and more measurable, let's say, with your eyesight and common sense, is kinetic energy. Okay, when an object has energy from moving, that's called kinetic energy. Associate the word kinetic with motion. Kinesiology, for example, kinesiology classes are these exercise type classes, sports type classes. So anytime you see that word K-I-N-E, you want to associate that with motion. Okay, so kinetic energy is energy of motion. How much energy an object has from motion is maybe actually not as intuitive as you might think. You might think that if something's moving twice as fast, it would have twice as much energy, but that's not true. Okay, kinetic energy is 1/2 times the mass of the object times its speed squared. Okay, so if you double the speed of an object, okay, if I were to throw an eraser at a sleeping student's head to try to wake them up, and if I were to throw it twice as fast, it would have 4 times as much kinetic energy, or 4 times the ability to do work. Okay, remember, energy is the ability to do work. Okay, so again, kinetic energy is somewhat noticeable and intuitive. If somebody were to throw a baseball at your head, you would know to get out of the way, because you would know that that object, that baseball, the fact that it's moving at your head, somebody threw it and it's moving towards your head, that it has energy, and the baseball would have the ability to do work on your head. And of course, if the baseball is coming fast enough, it could do serious work on your head. It may even cause you to get a cut or a bruise or a concussion, whatever. But again, doubling the speed of the object would give it 4 times the energy. Tripling the speed of the object gives it 9 times as much energy. So the kinetic energy of an object in joules is equal to 1/2 times the mass of the object in kilograms times its speed in meters per second squared. So you take the speed of the object in meters per second and you square it times the mass times 1/2. That gives you the kinetic energy of a moving object. Now let's look at a crazy example from the late 1800s, right around the turn of the 20th century. In Waco, Texas, William Crush parked 2 locomotives at opposite ends of a 6.4-kilometer long track, fired them up, tied their throttles open, and then allowed them to crash head-on at full speed. Why someone would do this, I guess it was for entertainment. He had about 30,000 spectators, so he's got pretty much a stadium full of people standing there. And of course, hundreds of people were hurt by flying debris. Several were killed. Of course, the kinetic energy here is fantastic in terms of the mass and the motion. If we do the calculation, it then makes sense why there was so much damage and so many people hurt. You got to remember, these are days when there was no TV, there were no movies. People probably these were the kind of community events that were exciting and people went to see, and so it's pretty spectacular that he had 30,000 people there, but it also makes some sense. Now, assuming each locomotive weighed 1.2 times 10 to the 6th newtons, that would be 1.2 million newtons. And its acceleration was a constant 0.26 meters per second squared. What would be the total kinetic energy of the two locomotives just before the collision? Well, let's calculate this out. Using our kinematic quantities, or kinematic equations rather, we know that the speed squared, final speed squared, would be equal to the original speed squared plus 2 times the acceleration times x final minus x original. Here we know the train started from rest. The understanding from the problem was that they went through a distance of half the initial separation, assuming they were going at the same speed. So each train would have moved through a distance of 3.2 times 10 to the 3 kilometers, or about 3.2 kilometers. And of course, that yields an answer, as we see right here, of 40.8 meters per second. Now, is that fast? Well, remember, 25 meters per second is about 56 miles per hour. So yeah, this is pretty fast. Now, as far as the amount of mass each vehicle had, we were told in the problem that the mass was 1.2 million newtons. Of course, we have our value of g here, 9.8 meters per second squared. Remember, near the surface of the Earth, which is pretty much almost all the time, unless you're in orbit, a satellite or something, then the mass would be equal to the weight divided by g, or 9.8 meters per second squared, and that gives us a value for the mass of the engines of about 1.2 times 10 to the 5th kilograms. Remember, a kilogram is about 2.2 pounds, and so these things weighed, what's that going to be? Maybe 250,000 pounds each. Now, we look at the kinetic energy. There's two trains, so we have to multiply our kinetic energy by 2 down here. The kinetic energy of each train would be 1/2 mv squared, so 2 times a half. Basically, we just take the mass of the a train engine here times its speed squared, and we end up with the kinetic energy, total kinetic energy we'd have in this problem, and we get an answer here of 2.8 times 10 to the 8th joules. That is about 200 million joules of energy. And so it's pretty similar to having a bomb, just a huge bomb explode. And that's, of course, why people were injured as the trains collided. So let's pause again and just double check your understanding of this. Just have you run through a couple real simple calculations of this to try to get it ingrained in your mind. Here we see a fire truck with a mass of 1,000 kilograms, and it's moving at 4 different speeds in the diagram. And I want you to calculate the kinetic energy of the fire truck in each case, and then plot it on the screen over here where the graph is. You want to plot your final answers for each of those, and then kind of connect them with a smooth line, and then answer the question. Okay, so you can pause the slideshow here and do that, and then we'll pick back up. Assuming you did your calculations right and read the scale on the graph right, the kinetic energies for the fire truck are as shown, and you'll notice again when we double the speed of an object, its kinetic energy quadruples. It goes up by 4 times. And so in your graph at the right, notice that the kinetic energy was asked for in joules, thousands of joules, and so when you plot this, you get a nice, you get a curved line. In other words, the kinetic energy goes up faster than the average everyday person might think. Most everyday people that don't know their physics would think linearly, think if I double the speed of my car, I have twice as much energy. But we see here that is not true. Doubling the speed of our car actually gives us 4 times the energy. Now, of course, everything that you're learning is helpful to passing this course and helpful in your engineering and science futures. But it also has some practical applications, and it's important that we, as we learn about things in life, that we take the knowledge that we've discovered and learned that are truths, things that we know are now true that we didn't know before were true, that we take that and let that affect our lives and the way we view things and the way we see things and the way we deal with life. So here's a practical application. Now in everyday life, most of the car trips that we take, if you drive, you're probably 10 miles or less. Most of the time if you're going grocery shopping, you go to a grocery store that's somewhere close to your home. Most people don't drive to the next town over to go to the grocery store or the barber or the doctor, things like that. You usually stick to things that are in your town. And so most of the trips we take in our car each day, let's say, are 10 miles or less. So let's look at a 1,000-kilogram car, and let's look at taking that 10-mile trip at 60 miles per hour versus 50 miles per hour. Now, if you're good with your math and your understanding of time, rate, and distance, then at 60 miles per hour, moving at a mile per minute, that 60 or 10-mile trip at 60 miles per hour would take you 10 minutes. At 50 miles per hour, that trip's going to take you 12 minutes. So it is true that by going 60 miles per hour, of course, you can get the trip done a couple minutes faster. You would save 2 minutes of time by going at 60 compared to 50. So we'll call that a positive thing, save 2 minutes of your time. On the other hand, though, that as we get into the kinetic energy, we notice that at 60 miles per hour, and again, if we do this in standard units, taking the mass of the vehicle here in kilograms and the speed in meters per second, then as we do this calculation, we get about 359,000 joules at 60 miles per hour versus only 250,888 joules at 50 miles per hour. So that's a ratio of about 1.43. So you have about 43% or 1.43 times as much energy at 50 miles per hour as you have at 60 miles per hour. Now, your braking force, remember when we talked about friction, we know your braking force does not get larger just because you're going faster. If you slam on your brakes and skid to a stop, the amount of braking force you have is the same regardless of how fast you're initially going. So if we look at this in terms of taking energy away from our vehicle, the brakes are going to have to do negative work, to take energy away from our vehicle. So in this particular case, if we have 43% more energy, then it's going to take 43% the distance in order for us to stop. In other words, 1.43 times the distance it would take to stop at 50 miles per hour, it would take us to stop at 60. So 60 miles per hour, we're going to need to say if it takes 100 feet to stop your car at 50 miles per hour, it's going to take 143 feet to stop your car at 60 miles per hour. So you're going to have about 1.43, just looking at random things, let's say jumping onto the road, you would have about 43% more accidents due to not being able to stop in time. You're going to hit, your hitting zone or your danger zone has increased by 43%. Now, since you're going down the road faster, as well, you have less maneuverability. You know that driving your car at 60 miles per hour, you can't swerve around something, wide. You can't take a wide turn going that fast, or your car will just roll because of the inertia. You'll tend to want to keep going straight, and your car will just start to roll and you'll crash. When you're going slower, you can weave, or you can turn around an object that comes out onto the road. So just looking at it from a common sense point of view, you have less maneuverability. That's a tough thing to kind of factor in. But we also know that you have less time to react. Going at 60 miles per hour compared to 50, you have less time to react and hit the brake. So your distance, your time there is about 20% larger, just in terms of your reaction time, the amount of distance your car goes before you can react. And so that increases by about 20%. So when we look at all these factors and put them together, the truth of the matter is you probably have well over twice the chance of seriously injuring yourself or killing yourself or someone else in a car accident for the entire 10-minute trip compared with what you would have during the 12-minute trip. So in other words, yes, you're going to be taking your trip for 2 minutes less, but the entire 10 minutes you're going to be having over twice the chance of something really bad happening. So, if you liken that to just random objects falling from the sky that could crush you and you need to get to your car for safety, you're out in a hailstorm, most people would say, well, it'd be better for me to take 12 minutes to get to my car with half as many of these things falling down than for it to take me, 10 minutes with twice as many of these things falling down. I mean, just statistically, if you think about it, your odds are much better. So it really doesn't make sense on short trips most of our everyday trips to speed. It really, most things in life, if you're 2 minutes late to a doctor's appointment or 2 minutes late to the dentist or 2 minutes late to the grocery store, life will go on, and most people don't, a lot of people's watches aren't even set within 2 minutes of each other. So it kind of makes sense to not speed on short distance trips in our daily life. Now, again, I'm not talking down to you. This is, I've been known to go over the speed limit myself. I'm simply saying that when we look at the physics of this and we apply it to our everyday lives, we see that speeding doesn't make sense in terms of everyday life. Now, I mean, if you're going to drive to Florida and you think, well, if I go a little over the speed limit, I'll get there a couple hours sooner, then, and if the highway is smooth and straight and the weather's good and you've got fences to keep wild animals from jumping on the road and things like that, then, the statistics start to, you start to think about time saved versus increased risk and so forth. So, I'm not going to judge all these situations, but we do know that in everyday trips, our short everyday trips that we make to and from campus, to and from work, that kind of thing, it really does not make good sense to speed. So far, we've been dealing with forces that are pretty much steady. At least we've been modeling them as steady forces while the object's displaced. So what do we do if we get a variable force, a force that fluctuates or changes as the object moves along? Well, in this case, we can divide the area under the curve of f of x into a number of narrow strips of width x, which are small enough to permit us to approximate the force f of x as being reasonably constant over that time interval. So as you see over here on the diagram at the bottom right, we basically take the variable force and we divide it up into little sections of parallel bars, and we can calculate then, imagine each of those little sections, delta x, as the force being constant during that time period and taking kind of the average value of it. Of course, if we do that and we add those all up, we get essentially the area under the curve. And so that area under the force displacement curve, and the displacement here, delta x, should really probably be considered delta d, or d, because that's the displacement while the force acts. That would be the sum of the work, or that would be the work done by the variable force in this particular case. And we know that if we take that to its limit, if we take the delta x value and we make it smaller and smaller and smaller, we end up with our calculus situation where delta x goes to 0. And as we take that limit, we get what is called an integration. We get the area under the force displacement curve, and we get the exact answer by taking an integral of the force, the variable force, as a function of its displacement, or as a function of the object's displacement as the force acts. So here we see in the at the bottom of the slide, in this case, that when we take this limit and we, as delta x approaches 0, we end up with what's called an integral of f of x dx. And we integrate that from the initial position of the object when the force acts through the final position as the force acts. So assuming we have a position that's changing only along the x-axis here, the object sliding along the horizontal direction as this force f of x acts, and the force f of x varies as a function of displacement as shown in this curve, then what we end up with is the work done by that force. And so how do we integrate? Well, we're going to talk about that in just a minute here. So as we look at the equation here, remember that force equals mass times acceleration. So interestingly enough, if we take this relationship, this integral, and we replace f of x with m times a, mass, assuming the mass is constant, that would come out in front. And so acceleration is dv dt. And if we say that we take dv dx times dx dt, that would be the same as taking dv dx times v. And so dx times dx would just leave us with a v dv. In other words, what we'd end up with is that the work integral is the integral over velocity from v initial to v final of mv dv. And again, m being constant, it can come out in front. And we would just integrate from v initial to v final v dv. And of course, when we integrate, the method of integrating is the opposite of differentiating or taking a derivative. So if we have something that has a power, let's suppose we have, for example, an x squared. Whoops, let me choose a different color there. That's not a very good color for showing on the slide. So if I take x squared and I differentiate, or I take the derivative, we know we take the power, multiply out front, and lower it by 1 power. So that's taking a derivative. Okay. The process of integrating is exactly the opposite. For example, if I wanted to integrate 2x, then what I would do is raise the power by 1 up here and divide by that number out in front. So for example, if I had x cubed and I was going to integrate x cubed dx, then the process is to raise the power by 1. So I would have x to the 4th, and then I would divide out in front by that power. So I would be taking 1/4 times x to the 4th power. That would be the integral of x cubed dx. And then, of course, I would have to, fill in the values, x initial and x final, and finish up my integration. So again, this will become clear as we go along. We will practice this more throughout the course, but basically this is what we call the work energy theorem. So the next lecture we'll kind of pick up with this idea right here, the work energy theorem, which basically says, if you look at this, 1/2 mv final squared would be the final kinetic energy, 1/2 mv initial squared would be the initial kinetic energy. So the difference in the kinetic energy from the end to the beginning, which is what we would just call the change in kinetic energy, the change in kinetic energy is equal to the work done. And this is called the work kinetic energy theorem. And we are going to talk about this picking up, and we'll get more numerical with it, picking up in the next lecture. So at this point, you can take a break if you need to, and we will pick up with the next lecture.